Hi there, and welcome to another episode of Mr. Carlson's Lab. Today we're going to take a look at an interesting device from, I'm guessing, the early 40s era. I'm really not too sure because there is no literature or information available on it, but it looks to be around that area. So what I'm going to do is open this thing up, and that'll give us a better idea of when this thing was put together and should get a little bit closer to the date. So what this device does is, well, first of all, it's a Sylvania electronic switch. And this thing's intention was to give very early oscilloscopes dual trace capabilities. So, way back when, this is, some pretty special stuff, especially, in the 40s era. So I picked this thing up off of a ham swap meet table, and I'm really hoping that this thing isn't a charcoal briquette inside. If it is, we'll make it work anyways, but, it's just a little bit more work if it is. So hopefully it's in good condition. What we're going to do is go through the thing. I'll probably end up drawing a schematic on this thing or something so that I can explain it a little bit better. And I'll restore the thing. We'll try it out with an old oscilloscope and see how well this thing makes two traces on a single oscilloscope screen. So let's get started. Here's a closer look at the face of the electronic switch, and as you can see, it's in pretty nice condition aside from a whole bunch of surface dirt on the top of the cabinet as well. Nothing that a mild detergent really wouldn't fix. Unfortunately, somebody was overzealous with a tested stamp. It says tested here, here, here. There's some red printing here that's smudged that's the same color as the tested stamp and up here as well, so must have been a slow day somewhere. Right above the model number here, where it says Type 104, the number 116 is stamped on the top here, and it's a really nice job. Right above the Sylvania is the letter B, so I imagine that that's a serial number. There is no other writing or printing on the outside of the case than, other than what's right here. So maybe the 116th one that's been made. This came from the industrial apparatus plant, so I imagine that this was intended to be in some form of an industrial application. So I'm expecting, pretty good build quality inside. This switch is probably close to the first of its kind, and I imagine, this was new technology back then, so this thing was probably worth a fair chunk of money. Down on the bottom here, we have a tag that really doesn't mean anything. This could have been put on at any point in time. It says OK and then a number 22. This is a ground lug on the bottom here, so our ground binding post. We have an input binding post A and an input binding post B. You'll notice that they don't use anything like a BNC jack or anything on the front of these units, and that's because back in the day when these oscilloscopes were out, they just used wires to tie into the oscilloscope, so basically twisted pair. Now this is going to be a low frequency device. I imagine it would probably be within the audible range somewhere. So this would be a common ground. So if we were to have a twisted pair running to input A, it would be like this, and then to B would be like this, like here. So you would tie the grounds or the commons together and put them onto the ground down here. I don't know whether this is isolated from the case or not at this point. It looks like there's some form of a wafer in behind here insulating it from the case, but we'll find that out here in a little bit. This would be the output side. We have ground here and output. So this is the output's going to go to the vertical input on an oscilloscope, and the ground would just go to the oscilloscope ground. We have gain A and gain B here. So this is obviously going to set the gain of A, input A, and set the gain of input B. Where in the chain of events these are tied in on the inside of this box, I really don't know at this point, but we're going to find that out together. They have different colored chicken head knobs on the gain A and gain B than the rest of them. I don't know if it was factory like that, but it does look nice, and I'll just leave them on there. In the middle here, it has a balance control. So this is obviously balancing something out inside. Maybe to balance out gain A and gain B so that, the signals rise evenly and fall evenly. At this point, I really don't know. Again, we'll find this out. Green jewel lamp on the front, most likely to indicate the power on and off. Range control for an oscillator inside and a frequency adjustment. So to give you an idea, say this was in range 3, okay, and we were to put this down at the bottom, that would mean that this is at the bottom of range 3 or the top of range 2. And then if we turn the frequency control all the way up to 100, that would mean that the frequency would be at the top of range 3 or the bottom of range 4. So you can see we'd have quite a range by using all of these different settings here. So obviously some form of a wafer switch inside, probably capacitors on it or something like that, set up somewhat like an old oscilloscope would be set up. Again, we'll find this out when we look inside. So the line cord here is in pretty bad condition with a plug here. Look at the plug. So, you know, this might actually be a blessing in disguise, you know. So I imagine the rubber got hard, somebody stepped on it and cracked it. So if this happened, hopefully a long time ago, that would mean that nobody has tried to apply any power to this thing and possibly burn up the power transformer in here. A lot of people like to plug these old devices in, old radios and old test gear, just to see if the jewel lamp on the front glows. And while the jewel lamp is, comfortably glowing on the front, smoke is, starting to pour out of the side because the high voltage section is shorted or something like that. So I'm really hoping that the power transformer and everything inside this thing is in good condition. Hopefully this, it's really heavy. Hopefully there's no rocks or charcoal in this thing. So we'll find out. Again, it looks, like it would be a pretty pricey device back in the day. In fact, this here feels like it's actually standing off of the paint here. So, yeah, so same with this here as well. So anyways, again, it looks like it would most likely be a relatively expensive device way back when, so probably a nice build quality. So again, what we're going to do is get this thing working. If it's not working, not a big deal, we'll make it work. I'm not really too concerned about that. I have lots of power transformers and whatever. It just means that, we're just going to spend more time in this thing together. And this is going to end up on that older test bench that I've been talking about in my other videos. Now, in some of my earlier videos, I mentioned that I'm putting an older test bench together with lots of old test gear, and we're going to service newer, modern devices with this really old test gear, and we're going to also use this to service, gear of the day. So, service old radios back in the 30s and 40s and things like that. The only thing that's really different about the test gear of yesteryear and the stuff nowadays is, of course, the new stuff is more bells and whistles, and you really don't have to think all that much to use it. This older test gear requires quite a bit more brain work to operate. And I'll show you how to work all of this old stuff, and again, we're going to fix things together. Again, the actual test bench that I'm putting together is taking some time, just because, just daily life, right? I'm trying to get everything all together here and get this other, I guess you could call it secondary lab put together. But it is coming along. It's a slow process. And as I find time, I just work on it, put a little bit of time in here and there. So this will be in a completely separate room with a whole lot of other old test gear. And we'll do some pretty neat experiments in there as well. Again, coming in the future. So what I'm going to do now is turn this thing around. We're going to take a look at the backside here, and I'll probably cut the cord off because, this is in pretty ratty condition. And we'll just go inside the unit here and see how the thing looks and determine what we're up against. This is the back of the unit, and it looks like these are the only two screws that are holding the case on. So I'll remove these and we'll go inside. But the first thing I'm going to do is get rid of this line cord. So it's out of there. It's a pretty ugly looking line cord. So, remove these two screws. Of course, they are fine threads. I'm glad I'm using this. Okay. Get that out of here. Let's see what we've got. Man, it feels like it's going to come off. Heavy little device. It's looking like some pretty good build quality already. Man, that case is heavy. That's easily 12 gauge steel on that case. That case is probably half of this thing's weight. Wow. So let's take a look at the top first. So the first thing I can see is we've got a bunch of goat shields. So these are spelt G-O-A-T, like the Billy Goat. And what these do is these just shield the glass tube underneath so that other things can't interfere with the tube and vice versa. These can't interfere with other things. So just a big metal shield over the top of the tube, that's all. Very easy to get off. Just pull the top cap off like this, take the cap off the top of the vacuum tube, and split the shield apart, and away you go. You can just pull the vacuum tube right out. So there's two of them there. The tubes are 6J7s. Now 6J7 tubes are pretty common in older radio receivers. They're used as mixers. So they're using these obviously for some form of mixing. 6K6s were used as audio output tubes in some of the earlier receivers as well. So what they're doing with these on this chassis right now, we'll have to find out. There's a 7N7 in the center here. This is a Lochtel type tube, so that kind of gives us an idea of the date, possibly of the, when this thing was put together. We'll look a little more into that. I don't want to say anything yet. So a 7N7 is a dual triode, so they're most likely using this tube as the oscillator. Now, a little trick with the 7N7 or any type of a Lochtel tube is they've got a dimple on one side. So these are known as octal tubes. They have an indexing pin in the center, so you can only put these in one way. And that is the indexing pin. You can see the little index there, I hope. All right, so that what you do is you just put them on the top here, give them a slight turn, and they'll kind of fall, and then you can just push them in. Well, these are a little bit different. They lock into place, and this really became a favorite amongst automobile manufacturers for their car radios. So the secret is the little dimple on the side. In order to get these out of the Lochtel socket, you bend the tube towards the dimple, and they kind of pop out, just like that. And it lets off, and you can see that there is a little ring on the bottom there, and that locks the tube into place. So in the older car radios, these things would be held tight in the socket and they wouldn't vibrate and fall out. And there's the little dimple. So if you're ever going to remove a Lochtel tube, these are also, in Philco radios and things like that as well. So if you're ever going to take these out, always just bend the tube towards the dimple and then pull up, and it should release it from the lock. That's what the little dimple's there for. So there it is. Rectifier, what is that? 5Y4, so full wave rectifier. Over here. And we have two filter capacitors. These are rated at 40 microfarads at 450. So these will be replaced with two 47 microfarad capacitors. They're both the same thing, it says there. And it looks like somebody's replaced one of these BRs. These are different. So we'll have to look into that. What else am I going to notice on the top before I move this? Yeah, it's really nice construction. The chassis is so nice and everything. Did a really nice job with this. On the bottom side, let's see here. What do we got? See if I got the light in here so it looks somewhat decent. So here's that wafer switch with a bunch of capacitors on it. And it has a solar sealed tight capacitors. And there's a 39 on there, which might date this thing. If I remember correctly, I think the Lochtel tube was introduced in late 37 or 1938. And this being 39, that might be a good way to date this thing. And of course with these tubes here, whenever you see tubes that have this kind of I guess you could call it a shoulder because that's what they're actually called. Sometimes they call them Coke bottle tubes. They have a whole bunch of different names for these tubes, but they're actually called an ST style tube or shoulder type, and that's what this is. This is a shoulder type. So whenever you see an old tube that's a shoulder type tube, you know that it's pretty early. Again, another shoulder type tube right over here, right? And it looks like all the tubes are still all original. Look at that. They all have an interesting little symbol on the side. It looks like a little leaf. Look at that. There it is there. Sylvania, Sylvania, Sylvania. And this one here is the same thing, a little leaf, Sylvania. So it'll be interesting to pull these two tubes out and see if they're Sylvania tubes as well. Maybe this is has really low time on it. But you see there's a 78 on this, and then there's also a stamp on this one here as well. So maybe this was just a replacement, or they were changing a batch when they were putting this thing together. 78. Looks like it says 78 on there as well. Very interesting. Maybe that is factory. So many things to take note of. So, yeah, bunch of capacitors, solar sealed tight capacitors. So, I don't know if you can see that there. It says sealed tight on there. You can see that on there. they're sealed tight to keep the leakage in. So you know that these things are horribly leaky by now. All of these will be all leaky, these wax ends on these things, so these will have to be changed. Same with these in here. So quite a bit of work to do in order to bring this thing back. Let's take a closer look at the bottom portion of the chassis and get a better idea of what the engineers were thinking of back in the day when they put this thing together. This really does read off like another story. So first of all, some of the easiest components to notice are these really big 1 microfarad capacitors. We've got 1 microfarad, 400 volts on this side, same on this side here. Now, if you notice something, if you were to divide the chassis into two here, you'll notice that we have pretty much two identical sides, and that's because we have two identical channels, channel A and channel B. Two sealed tights here, two sealed tights here, an electrolytic here, an electrolytic here, a bunch of resistors here, a bunch of resistors here. Now, you'll notice a size difference between this electrolytic capacitor and this one here, but they're both rated the same. They're both 4 microfarad. Now, the reason that they may have done that is just for size consideration, or they may have bought up a different lot of capacitors and they're just using them up. Way back when, they do the same thing that they do nowadays, is if they can get a better price on a different lot of capacitors, they'll do it just to cut their costs. So you'll notice this a lot in some of the early radios as well, the little early receivers. You'll notice, say, 4 7-pin miniature tubes, and then right out of the blue, there's like an octal converter tube or something like that in the chassis. And you're like, why? What have they done here? The reason being is they probably had maybe 100,000 octal converter tubes left over. So they just want to use them up. So what they'll do is they'll punch a larger hole in the chassis and put an octal tube in there instead of a 7-pin miniature. So very, very common. And in fact, you may have come across one of these radios. I've come across plenty that they've done that in, just different manufacturers. This is a filter choke over here. So this is doing some filtering for us, taking a little bit of ripple out. We have our fuse down here, line cord that we cut, another capacitor here. Here we have a large variable resistor of some sort. This is to be determined what they're doing. And a bunch of mica capacitors. So the micas most likely won't need to be replaced. These seal tights are going to have to go. These are going to have to go. These electrolytics are going to have to go. I'll test all these resistors. These are roundy type resistors, and a lot of the times they really move in value. So I'm going to check all of these. I want to make the channels very close so that we can get some pretty consistent results between two channels here when we're doing our experimentation. So I'll test these resistors up here, again, more roundies, one here and one here on this potentiometer here. So in order for me to really explain what's going on in here, I'm going to have to draw this up. So what I'm going to have to do is probably cut one end of these 1 mic capacitors and lift them out of the area. And I'll just draw up a schematic for this entire unit here, and then that way I can explain better what's going on in this unit. Just before I do that, though, we'll take a look at the top end of the chassis, a little closer look at that. Here's a closer look at the upper portion of the chassis. And you can see that we've got these goat shields here. I'll show you how to remove these. It's really quite easy. What you do is you just remove this top cap here. Now this is a grid cap on this particular type of tube, not to be confused with a plate cap on some of the transmitting tubes. The signal is going to be going in here, whereas on some of the larger power tubes, the plate cap is where the high voltage goes in, so you need to know the differences. You wouldn't want to be touching something like this unless you knew that the high voltage was discharged. Again, this is where the signal goes in. This is a grid cap, not a plate cap. So you just pull that off. And in order to get these out, all you do is you just hold onto the tube and pull the shield, rock it a little bit, pull the shield and the tube out together. They are in there pretty tight. Now, you got to be careful with these things that you don't cut yourself, because these are just basically stamped. And these edges are razor sharp on all of these things. So just make sure that you don't cut yourself. These things, they just split apart in two like this, and you get your tube out. And look at that. Sylvania, it's got the leaf on it as well. So when we look at all of these tubes here, they all have that little Sylvania leaf on them. Even the Loctile type tube here. So they're all the same. So with the Loctile tube, I'll just bend it towards that dimple there and take it out again. Even that little leaf on that one as well. The little lock. There's a better look at the lock on the bottom. And there's the indexing pin on this one here. So you have to align the indexing pin up. close to a loctile, or close to the octal type tube, but the reason they are called the loctile is because of this little area right in here that just snaps it down into place. So just like so, and they stay in. They're really quite a well-mounted tube, so very good for automotive use back in the day. So that's a look at the upper portion of the chassis. There's that VR on the other side. See how these all have this red number on it? This has got, looks to be like a 78 or 76. It's kind of smeared, hard to say. Same thing over here. So again, maybe they're just using different lots of components. So they may have bought up a bunch of, again, different lots, and they're using up this one here and this particular style over here. A few hours later, well, more accurately, about 3.5 hours later, we have a schematic for this entire device. This is everything that's inside that little electronic switch. Now, whenever I go about reverse engineering something, whether it be vacuum tube or solid state, what I do is I just pick a corner. I start with pencil and paper and just an eraser, and I'll start drawing. So I usually pick an extreme end of a circuit. So at this point here, I started at the 6J7 and I worked my way towards the 7N7 oscillator. You could start at this end and work this way as well, just whatever you're comfortable with. You'll find when you start drawing schematics on a piece of paper that sometimes things get a little bit too condensed because of just the amount of components. So you'll find yourself erasing things, spreading things apart, and then redrawing again. And in fact, I redrew the schematic a couple of times just because of component density. You'll see here the length of the screen grid line has to come way out to here so I can draw these two components in, and then it runs out to the balance control. Originally, I started with, short screen grid leads, and then you find that, I got to add a cap and a resistor in, so you erase it. And then after a while, the schematic starts to look ratty, so then you just start over again. And this is just standard stuff whenever you're reverse engineering. And of course, while you're doing this, you're trying to keep this as clear for your own reference as possible. And in this case, I'm trying to keep this as clear for my reference and yours as well. Now, after I'm finished drawing an entire schematic, what I do is I take that and I photocopy it, and I turn the pencil into basically black ink. Reason being is because graphite glares in the camera. Now, I've drawn in one resistor value in graphite, and you can see the result. I'll just lift the corner of the paper, and it does that all the time, and you can really see how some of the graphite will even try and blend with the paper. And you can see that it's fooled this line here, it's fooled even the copier a little bit. It's gotten really pale, but this is actually a really dark line. This is just standard. I guess it's just the way that the pencil creases the paper while you're doing your drawing. So at any rate, so that's what I do. You can tell that this is a photocopy because this is a line over here. And then after I've done this, then it's pretty much ready to present. Now I could take the time and draw this out on my schematic program and really spend a lot of time with it, but this is completely, I can completely understand this, and it's pretty clear. So not only that, the amount of time involved in that would take quite a while as well to redo this. And then if you're going to redraw this in a schematic program, you have to find things like range switches with 4 positions, something that can be ganged and things like that. So just draw it as clear as possible, and I just usually end it at that point. At any rate, so when you start reverse engineering either a point-to-point device or a solid-state piece of equipment, sometimes you're going to find components that are in the way, and in point-to-point devices, that is very common. For example, these capacitors, there's 2 of these. There's this one here and this one over here, and they cover up a lot of the circuitry that's underneath here, basically hiding things. So in my case, I'm just going to replace these, so I just took these things out. Now, if you're uncomfortable with completely removing components during a reverse engineering process, you can desolder one end and then bend the component up and then look around it and draw everything. And then if you're careful, when you bend this thing back, usually they fall right back onto the area that you've desoldered it from. So that sometimes makes things a little bit easier if you're uncomfortable with completely removing a component. One thing that was really an issue with this one here is this 7N7 tube socket is completely under all of these capacitors on the range switch. So it looked like a cluster of wires running to the 7N7 tube socket, just a big jumble of wires into this little area, and then that was it. You really couldn't see much of the tube socket. So in order to reverse engineer something like this, you would want to remove everything out of the way, much like I did, so that I can have a clear view of the socket, and then I can follow each wire directly to the pin. Another thing that's a little bit of an issue with Lochtel type tube sockets is from the bottom, sometimes it's a little bit hard to indicate where the locking pin is because it kind of hides above the lock. They're not as easy to spot as an octal type tube socket. So that's another thing, you got to locate the locking pin or the index on the locking pin, and that way you'll be able to count pin number 1. When you look at the bottom of a tube socket, the tubes always start from the index. If the index was here, this would be pin 1, 2, 3, 4, 5, 6, 7, and 8, and then you'd be back at the index pin again. So you always count clockwise on the bottom portion of a tube socket. No matter what vacuum tube it is, you always count clockwise on the bottom. So how this schematic works is, if you look at the 7N7, the 7N7 tube is nothing more than a 6SN7 tube packaged in a Lochtel type package, really is all they've done. So they've taken the guts out of a 6SN7 and put them into a Lochtel type tube. The reason that they've done that is so that they can make a rugged version of the 6SN7 that won't pop out of its tube socket in mobile use. That's the reason that they did that. So 6SN7 equals 7N7, same tube, just different base, that's all. Now if we look at the 7N7 tube here, you can see we have one triode on this side and another triode on this side. You'll notice that the grid of this triode connects to the plate through this capacitor, and you'll notice the grid of this triode connects to the plate of this capacitor. This makes a nice little oscillator that will go back and forth like this. Now from pin 6, we have a 1 microfarad capacitor, that was these really large capacitors here, acting as a DC block, and that's connected to the control grid of the 6K6. The 6K6 tube is a power pentode, and I haven't drawn in the third grid. The third grid is the suppressor grid. There's no reason to draw that grid in, just because it's connected internally to the cathode, and you'll notice a lot of these tubes, 6K6s, 6V6, 6F6, all that, they all draw these particular tubes, without a suppressor grid. Now, mind you, some of those are classified as beam tetrodes and things like this. But the 6K6 is a pentode, and just for ease of understanding, I've drawn this as a tetrode. You'll find this in a lot of schematics, they do this, just to make things a bit easier to understand. So the 6K6 itself is triode connected. Whenever you hear the term triode connected, all that means is they've tied the screen grid to the plate, and they've basically using it as a triode. The 6K6 is configured as a cathode follower, and since this is a power pentode, this is going to be a pretty stout cathode follower. So what's going to happen is we're going to have an oscillation going back and forth here. This is going to block the DC from the plate, but it's going to allow that pulse to come through. What's going to happen is we're going to get a pulse onto the control grid of the 6K6. The 6K6 is going to turn on because if you bring the voltage on the grid positive, the tube is going to turn on. Now, when a vacuum tube turns on, if you want to picture this mechanically, you can picture the cathode trying to connect to the plate. So it's trying to act like a switch. It's trying to connect this to the plate. So more so like a big variable resistor, the more voltage you put on the control grid here, the more this is going to try and conduct. All right. So what's going to happen now is we're going to receive a pulse here. The plate voltage here is going to try to connect to the cathode. It's going to lift the level of the cathode here. You'll notice that the cathode of the 6K6 and the 6J7 are tied together on both sides through a 2K resistor to ground. The cathodes have to be tied to ground because the tube needs some form of a ground reference, so it's tied to ground, and the 2K lifts the cathode off of ground to apply some bias to the circuit. Now, what happens with a vacuum tube, and a lot of people get confused around the biasing of vacuum tubes, and I'm going to go through this in the future. I'm going to spend an entire video episode just talking about biasing up power tubes and triodes. And I will also in the future go through a video about reverse engineering as well. I meant to mention that earlier. I'll pick an easy vacuum tube circuit and we'll reverse engineer it together. And I'll also pick an easy solid state circuit with a circuit board and we'll reverse engineer that too. And I'll show you the steps in doing that. A lot of people think that point-to-point wiring is much easier to reverse engineer than circuit board stuff. Actually, it's quite the opposite. A lot of circuit boards, you can shine a light in the bottom and look right through the circuit board and see the traces on the other side, providing there's not a big ground plane layer and hidden vias and things like that. Most of the time, it's very possible to do that. Whereas this, you have wires hiding behind things. They're coming up behind boards and being tied in odd places. You know what's even really bad about some of these manufacturers is they put looms of wire together with the same colored wire, and we're talking like a loom of 25 wires. And they're just loomed together all the same color, so you have to ohm things out. So my own experience, reverse engineering circuit boards, solid state equipment, the modern stuff, to reverse engineering this old stuff. Actually, the old stuff is a little bit more time consuming to reverse engineer. At any rate, getting back to the schematic here. So we have both of these cathodes tied together, and they're lifted above ground here. All right, so it's going to be applying some bias to these tubes here. Now, when you lift a vacuum tube above ground, say that there's 8 volts on the cathode here because it's going through this 2K resistor. We'll just use that as an example. Say there's 8 volts on the cathode. That looks like negative 8 volts to the grid because you're lifting that above ground. So it looks like negative 8 volts on the grid, and that's what they use for bias. That's the reason that you see cathode resistors on vacuum tubes. It's just to bias that stage up. When you see a capacitor across the resistor, basically it's just acting as a bypass capacitor. So it's allowing a path for the AC to flow. That's what's happening here. So in this circuit, we have 2K lifting both of these tubes up on this one side. We'll just focus on one side for now. So what happens is when this is lifted above ground, it's basically putting this at a point to where the tube isn't completely off and it's not nowhere being completely on. It's just at a comfortable point. If you want to look at it again in a mechanical term, you can kind of look at it like a stall converter in a race car or something like that. So when you're at the line on a racetrack, you bring your car up to its stall. It's at that point to where the car is not idling and you're not giving it full power. It's just at that point to where it's ready to go as soon as the tree comes down. You can look at it like that if you want. And that's what's happening with the tubes. It's bringing these tubes to a perfect point to where it's very easy for the tube to transition from the on to the off cycle. All right, that's basically what's happening. That's what bias is for. Now what's happening is when this tube receives a pulse, what's going to happen is it's going to try and connect the high voltage here from the plate line. It's going to try and connect that to the cathode, and what it's going to do is it's going to lift this tube up. All right, it's going to lift it way above ground because this is going to go positive. Say it's sitting at 8 volts, for example. So when this receives a pulse, this might take this up to, say, 25 or 30 volts. Well, when this tube gets lifted to 25 or 30 volts, what's going to happen is it's going to bias this signal off. So basically the tube is just going to shut right off. So it's going to ignore the signal that's coming into jack A over here. All right, when it comes to the transition, so when this is basically the tube shuts off over here, this is going to drop down again, and it's going to allow this signal to go through. So you can see how that's basically gating this signal. So you can look at the 6J7 as somewhat of a mixer tube. It's receiving a pulse on the cathode to basically change its level, lift its level up, and it's shutting this signal on and off and on and off. And it's doing that back and forth between these two channels so that we can get 2 traces on a screen. So if we look at the balance control over here, what's happening with the balance control is this would have been more accurately labeled as trace position. So what's going to happen here is as we move this control here, this is bringing B plus here, up here, this is a screen set, so basically maximum screen voltage only. You can set this so that you don't give too much screen voltage to the tubes. So through this, what's happening here is when you move this closer to this side, the screen voltage is going to go up on this tube. When you increase the screen voltage on the 6J7, the tube is going to want to conduct more. All right, so basically what this is doing is this is allowing the tube to be turned on more. When the tube is turned on more, it's going to pull the plate closer towards ground. As it does that, it's going to shift the trace on the screen. So what's going to happen is basically this is just going to allow us to move traces on the screen. Why they called it balance is kind of odd. I figure what they've done is because we have a square wave, all right, so we'll have basically a signal here, and it's going to be doing this. And then if we have a little bit of signal on the square wave here and here and here and here and here, and it's moving around, what we're going to want to do is play with our scope settings and make this portion of the square wave larger so it appears as one trace. And then we'll do it with the other one as well. Now, what's going to happen is we have a square wave. Now, if we bring this to the center, basically what's going to happen is it's going to balance this out. So basically it's going to look like the two traces become one trace right at the center here. And that's maybe why they call it balance, because they balance it out. Again, I would have figured, trace separation would have probably been a better term. So that's how this circuit is working. And by looking at one channel here, we can very clearly see how the other channel is going to work. When this one's on, this one's off. When this one's on, this one's off. And it's just going to be doing this back and forth. And that's how we're going to get our dual traces on the screen. That's basically how this circuit works. Now at this point, I just drew this thing up. I don't have any voltages because I can't power the thing up yet. It needs to go through the resto. So I don't know any plate voltages. I don't know any screen voltages or anything like that, but I'll edit those in later on. Here's another thing. This is a DC coupled circuit. All right. And since this is a DC coupled circuit, we have the plate connection here. There's going to be high voltage on this. And if you look at that, it goes right to the output jack. There's no blocking capacitor. No blocking capacitor at all. Why have they done this? Basically just to keep the integrity of a square wave signal. So everything is DC coupled right into the circuit. You'll notice that there's no blocking capacitors. The only blocking capacitor you're going to see is between the oscillator and these two cathode followers over here. All right, so basically they're just acting as two large switches. So we should have some, a nice square wave going into this thing and making a nice trace. And that's really what it is. So at this output jack, I have to remember to be very careful or I might zap myself. There's a ground lug and an output. I don't want to touch both of those at the same time. And I'll measure these in the end. You'll see what I mean. You can see the high voltages here. It goes through this choke, through the 100K. We have a 40 mic capacitor here acting as more filtering and right through this 47K resistor right to the out. So high voltage right on the output jack. So if you ever find some form of a DC switch like this, this is something to keep in mind. Again, they're doing this to keep the integrity of that square wave. And we'll take a look at square waves too, see how well this does. Again, this is a low frequency device. So this thing is going to be very good with low frequency square wave. I imagine if we start, pumping fast square waves into here, we're just dealing with twisted pair, right? We're going to probably get, sawtooth looking square waves, but, at lower audio frequencies, it should be okay. So nonetheless, it's going to be fun to bring this thing back to life and use this in some future episodes. So that's it. 5Y4 full wave rectifier here. So you can see center tap here. This goes to ground, high voltage on this plate and this plate. And then we have our filament winding here, heating the tube. The center tap of the filament winding comes out, goes into this filter reactor. We have a 2 microfarad capacitor on this side, doing a little bit of smoothing. You don't want to put too much capacitance right here because then this thing is just going to look like a resistor. It's not going to be a reactor anymore. So we only have 2 microfarad here, which is allowing a lot of filtering to be done over here. And we have a 40 here and a 40 here. So what else can I tell you here? That's pretty much it. Filament winding, jewel light here. That's a little green light on the face, and this just runs to the heaters. I don't draw the heaters on here just because you really don't need to show them. One end of the heater goes to ground, the other end just goes to here. Again, just keeping complexity out of the circuit that doesn't need to be there. You'll notice that I did draw the suppressor grid on this one tube here, and that's because it has an external connection. So it actually comes out of pin 5, so I've connected it to pin 8 like it is there. Again, this is an internal connection in this tube, so I just drew this as a tetrode. And that's pretty much it. What else can I tell you? This selects the range. This would be the slowest range. This would be the fastest range, 0.01 being slow. These are ganged together and they move like this. All right, so you can see that it matches on both sides. And this would be the fine tune, or the trim between them. So there's two 4 meg potentiometers here ganged together, acting as that in between frequency control. I'll explain why I think that this thing was most likely a factory recall or some form of a warranty that might have even gone back a couple of times. So if you recall, when we first took the unit apart and we looked on the underside of the chassis here, you probably noticed that they had a little bit of ink or felt marker on every single solder connection. And when I first looked at that, I just thought, wow, that's some pretty good quality control, and really didn't give it a second thought, because it's everywhere. Every single lug on the tube sockets, everything has got this felt marking on it. You can see it. It's everywhere. Even the solder joints here. Everywhere that there's a solder joint, there is a little bit of felt. Now, when I started taking everything apart here and removing the parts and pieces, I found out that this particular capacitor was not even soldered. There is no solder on this whatsoever where it hooks onto the tube socket down here. So chances are one of the channels in this unit was very intermittent and caused this thing to go back to the factory a bunch of times until it got to the point where somebody said, check every single connection and mark it. And that's what they did in this unit. And you can kind of see their thought process, one channel being intermittent. Where might the problem be? So if we look on the top side of the chassis here, I have a bunch of solder rules supporting this thing so that it'll sit square on the camera. So if we look on the top side of the chassis here, this is the channel that would have been acting up. You can see they've marked all of the wires here as well. You'll notice that this is the potentiometer that they've changed. So you can see this one here looks quite a bit different than this one here. This looks like, the case of this looks much like this here, and the other potentiometer on the bottom. They've even marked the solder connection on the, the grid cap of the tube here. So very good possibility that this thing was a real troublemaker, and that would explain why this has such low time on it, probably because it was acting up, and that would explain why all the original tubes are still in the chassis here. Now, as I was doing this and taking the measurements for the schematic here, I removed the wires off of this because I couldn't get a very good measurement. This here is the same potentiometer as the one underneath the chassis. So when I tried to measure this, I just got funny readings and nothing was really happening. And I'm thinking that maybe there's something else in the circuit, maybe some capacitor or something that's causing some issues, because this is really before I started going after the schematic all the way. Right, this is about mid schematic. I did this here. So I measured this, and this potentiometer is completely open on both sides here. So I can go over to one side here, like to about this point here, and it starts to make connection. Right, and I have a few k ohm here down at the bottom, and then it opens completely to here, and then again on this side it has a couple of k ohms down to this side. So there's a whole bunch of wire here that's completely disconnected, and it's done it on both sides. So why it has basically blown almost evenly on both sides is really bizarre. Now, there are capacitors here. What's happening is this here ties directly to the screen grids of the 6J7s here. So we'll take a look at the schematic again. And you can see here that, the screen grids, they've got these capacitors, these 4 microfarad capacitors right to ground, and that's on either end here. So maybe what has happened is these capacitors have become very leaky. That would be these 2 capacitors here, this one right here, and this one right here. Maybe they became leaky and it just eventually destroyed this. So, yet to be found out. So very interesting. So this thing really does tell quite a story, and that might actually be the reason that this thing has this tag on it. Who knows how old this is? It says OK on one side, and it's written in red writing. I don't know if you can see that. It's kind of glary. It says OK there. So maybe this thing really never was okay, and it was just a continual troublemaker. At least that's what it's looking like. So anyways, back to this potentiometer here. This is on the back side here. It says M70 MP right here. Yeah, M70 MP. So if we look on the bottom here, and we take a look at this one here, there's another potentiometer here. So if we look at this one is the same, and it measures 70K with the potentiometer wide open. They've tied two ends of it here together just because of, they have this controlling the level of the screens. So what I'm going to do is I'll replace this one here with something suitable under the chassis, and I'll put this one here on the top side of the chassis, and I'll replace that screen control up here, or the balance control for the screens, I should say. I'll replace that, and it'll keep the upper portion of the chassis looking all right. Now, as I was on the upper portion of the chassis, I'm measuring this one, and they both are supposed to be 100K ohms, they say right on the actual case here, but this is supposed to be 100K ohms, but it measures 70. Now, you're probably saying, well, disconnect some of the wires. Well, this just runs us to an open jack. So from end to end, 70K and 100K over here. So what I've done is, I think I've got them around here somewhere, right over here. I've got two brand spanking new 100K ohm potentiometers, and what I'm going to do is just put two brand new ones in here. The shaft length might be a little bit long, so I might need to take a little bit of the shaft length off. It's kind of a universal fix, this one here. These are nice and smooth and brand spanking new. They just have a bit of solder on them here because I've used them for breadboard testing. But so I'll end up replacing these here as well. So I'll have a nice matched set of 100K potentiometers here. And when I'm putting this other one in here, what I'm going to do is carefully measure each side here, so each side from the center. And when I get exactly the same K ohm reading here, this says 70K ohm, but they're never really 70K ohm. So, just for example, say this was an 80K ohm potentiometer. I would want to read 40K from this side to this side and 40K from this side to this side, and that would mean that this is roughly, right in the center. So when I have this potentiometer here centered, the new one centered, what I'll do is I'll put this right in the center, and this will be a very good indication of how well balanced everything is in this circuit when it's put back together. At this point, I'd say I'm about halfway through the restoration. Now, I would love to have you guys with me through the entire restoration, just have the camera rolling as I'm testing and replacing components and removing things and verifying parts and things. But I would have hours and hours of footage just in that alone. Through the magic of a camera, this seems like seconds between each shot, but actually to get to this point was quite a bit of time. So at this point, again, about halfway through. Now on the top portion of the chassis here, I've removed both of the gain potentiometers here, and I've also shortened the shafts on the new ones. I haven't installed them yet because I'm going to clean the face here first with a mild detergent. So I'll remove these chicken head knobs here. I'll leave the binding posts on and everything else here, but I'll remove the chicken head knobs and I'll clean this up. This should come up really nice. So you can see the tested here that somebody's put on is a little clearer than before. There's that writing. There's the writing on the top rim here. There's the B, and over here is that 116 stamped there. So this should clean up pretty nice. Now on the back side here, I've also removed the potentiometer from the bottom and I've installed it here. So this is the one from the bottom portion of the chassis. The original one is right here. And it is quite faulty. So if we look at the potentiometer here, the first opening is, there's two little dots. There's the first one. The second one there is where it's open on this one side. And then if we look at the other side, there was a line. There's the line right there, and it was open right on that line. So odd, it's even area from each side, and then this whole area of wire in the top here is just, completely disconnected. Now, for those of you that have never seen inside of a wire-wound potentiometer, this is what it looks like. So what happens here is where the lead goes in, there's wire that's wound around a form all the way around here. The wire is very fine, like a hair, and it goes all the way around from one side to the other. This is the wiper that's connected to the shaft, and the shaft is insulated from this particular part here. You can actually see the insulator material here. So when this is down at this point here, there's really low resistance between these two pins right here. As you start to move the wiper up, this is rubbing along that wire here. As you get further and further from this pin right here, the resistance is climbing. and climbing until you get to the extreme end here. Now, what happens with these things is when a capacitor leaks or something like that, usually what it does is it just burns the wire up, and that's what it's done right over here and right at that little second dot right there. It's put 2 little burn marks there. Now, this really isn't repairable unless you want to spend a lot of time in here. Again, I couldn't even begin to imagine the turns count of wire in here. So, if you can see that, it's really even too fine to see any definition of the wire there. But at any rate, lots and lots of turns here. So when something like this is bad, you just go about replacing it. What I do is I usually throw these things in a bin. If I ever need parts down the road, I can get this shaft off here by removing this little clip, and the centerpiece will come out. There's spare parts and pieces. So if I have another one of these things that does have an issue that doesn't, involve this wire being open, I still will have some spare parts. And, I've thrown lots of this stuff away in the past, and, I've, pretty much kicked myself later on for not keeping it. So this is what I do. I just put this in a dead parts bin and, mark it as being open in 2 areas here. So anyways, that's how a wire wound potentiometer works. So if you ever want to test one of these things, or pretty much any potentiometer, if you want to see if it's good, usually what happens when a potentiometer fails is it opens somewhere along the resistive track. So all you do is you disconnect the potentiometer and just measure with your ohm meter from end to end. If you get a resistance, this one here would be 70 k ohms or close to, I know that the wire is still making connection from end to end. And then the next thing you do is you go from one end, so you'd bring this down here like so, put your ohm meter across it like this. You should have close to a dead short at this point, and then slowly advance the control while watching your ohm meter, and it should slowly climb as you turn this, and then when you get to this end here, you should be right at 70 k ohms when you're measuring this side. And it's the same with this side. This side would now measure a dead short because the wiper's at this side. So as you move it this way, this will slowly climb the resistance between these 2 pins all the way up to 70 k ohms at this end here. And that's how you test one of these potentiometers, or pretty much any potentiometer for that matter. So on the bottom portion of the chassis here, just grab a solder roll here to support this. There we go. So on the bottom portion, I've replaced these capacitors here, which were these ones here. So these are the new ones here, and they kind of nicely fit right into that little slot there, so it gets rid of these ones. These are the new electrolytic capacitors mounted here, so that replaces those 2 large cans on the upper portion of the chassis. This potentiometer here replaces that one that I've now taken from here and put it onto the top. In fact, this particular potentiometer is a pretty special one. I've got a bag full of them, but it fits the bill. It's basically 2 potentiometers controlled by 1 shaft. So you can go from end to end, and then it kind of hits a stop, and then there's a fine tune at the stop. And then if you go the other way, right to the other end, you'll hit a stop, and then there's a fine tune from that point. So it's a really neat potentiometer. Again, I had a bag full of these things, and it fits the bill. It's about the right wattage, about 3 watts worth right there. This capacitor here, this 2 mic capacitor, has been replaced with this 2 mic capacitor. And all the sealed tight capacitors, these guys, solar sealed tight, you can see wax molded paper. So this is a paper and foil type capacitor. You can see here it says outside foil. So I've mentioned paper and foil in many of my other videos, and people say, don't you mean paper and oil? No, these are paper and foil capacitor, and in fact, most of the capacitors from way back when are like that. So at any rate, bad capacitors, very leaky, again, sealed tight to keep the leakage in. Those are out of there, replaced by these guys right here. Newer style capacitors of the correct value. Now, this capacitor here was a 0.005 microfarad capacitor. A modern value that would replace that would be 0.0047. That's going to be just fine. No big deals there. They use a lot of different values in here that can be, replaced by a very close value. I've replaced the electrolytics here and here. The reason that they have heat shrink tubing on them is because they've been repurposed from an extremely high voltage power supply that I built some time back that I'm no longer needing to use anymore. The capacitors are all good, so I just used them. So I didn't need to take a trip into town to go any buy any of these capacitors here. So those are replaced there. What else can I tell you under here? Haven't used any contact cleaner yet. I plan on doing that. Still need to put in the line cord. Everything on the bottom portion of the chassis at this point is pretty much done, aside from contact cleaner and line cord. So all I really need to do is clean the face up at this point and put those potentiometers back in. I'll clean up the chassis, clean up the case, and at that point, when I'm ready to power this thing up, we'll do that together, and hopefully this thing won't make any smoke. And I think that's about all I can tell you right now. Haven't bothered testing the tubes. I'll just use the circuit itself to test the tubes. So a lot of the times, the best test for any vacuum tube is the circuit it lives in. And this is very true for most tubes. So what I did to this, in order to make this come out this incredibly shiny, is first of all, I took some 91% alcohol, and I went over this with a liberal pressure a whole bunch of times, really just to clean the surface and open up the pores of the paint. And then what I did is I took some swirl remover and went over this a few times with this swirl remover here. And then after I was done, I used some wax. This is just automotive wax, and put this on the top and buffed it out, and that's how it came out. Now the alcohol step for this was very, very important, and the removal of the face also was very important. If there's little nuts still applied to the face here, when you try and polish it, you're always going to have that little rim of dirt around there, and you can always see that, and that was really what made it necessary to remove this face to clean it this well. But as you can see, it turned out very, very nice, and it's got quite a shine to it here. I can almost see myself in it. So that's how I cleaned the face of this. Now, if you're working on older test gear, pretty much every different piece will react differently to different chemicals, and you need to be very careful. Always test everything you're going to do in a little inconspicuous area first before you go just, taking everything and putting everything right into it. For example, say this was a different kind of paint, alcohol might try to remove this, right? So again, you got to be very careful, and of course for each different piece of test gear, there's a little bit of a different process. It just takes a little bit of experimenting on the face or in an inconspicuous area where there is some paint, and before you know it, you'll be well into cleaning it up. The electronic switch is pretty much finished at this point. The only thing I need to do now is install a brand new line cord, and we can try the thing out and see how well it works. The thing really went back together quite easy. They really did their measurements well. The face on this thing is held on by these two screws, and the binding posts at the bottom have long shafts on them that are threaded, and you just put a nut on the backside, so the grounds are just chassis ground, really. And that's what holds the face on, these two screws and these two binding posts on the bottom. So to give you an example, I just basically lay the face back on, tighten these two screws up, and the two holes for each binding post perfectly lined up. They just fell right in. So they did a really nice job with their measurements on this thing here. Everything else is just kind of fastened to the face. Same with the light and all the controls on the top here. I installed two brand new potentiometers here, and I'll show you those in just a moment. One thing to keep in mind whenever you're putting the knobs back on a potentiometer with a non-indexed shaft. So when I say non-indexed shaft, I'm talking about a potentiometer like this with, it just basically looks like a piece of round stock. There is no flat area, so this is non-indexed. So you can pretty much install these things in any position you want, and then just align the knob and then tighten the set screw onto it so that it points to the appropriate area. So when you put the knob back on, you turn the potentiometer down to 0, put the knob at 0. If you tighten up the set screw, what's going to end up happening is it's going to move the shaft on the potentiometer. So what's actually happening here is it's acting like a gear set as you're tightening up that little set screw. So you have to offset the knob just a little bit, and then when you figure out exactly how much it's turning that shaft, it'll go right to 0 when you put this right back down again. And that's what happens here. So it does make things a little bit time consuming doing that. You could say, well, why don't you just turn it the other way and it'll pretty much hold it there. Well, as you can see, these potentiometers go past 100 at this point here, whereas they sit at 0. Even the factory one on the bottom on the frequency control doesn't go exactly right to 100. So it just depends on the potentiometers that they originally designed this thing with. These are very close. Like, I mean, there's just a little over 100. So these worked out very nicely. So something to keep in mind whenever you're dealing with a potentiometer and a non-index shaft. I'm going to show you something else that's a very good idea here in a moment as well. Something to keep in mind for any of your future builds. So what I'll do is I'll move the chassis around here. We'll take a look at the backside and I'll explain exactly what I've done. The chassis cleaned up very nicely as well. I used a mild metal polish, basically just to take off the oxidization here and to clean off the surface crud that's just settled on the chassis over the years. The side of the unit here has some slight pitting on it. I'm really not too concerned about that. It is really quite mild. Now, it's always a very good idea whenever you're cleaning a chassis like this, say you're going to use a metal polish, to try that in an inconspicuous area as well. You'll notice that there's some stamps on the chassis here that mark the tube numbers. So this identifies what goes in the socket. Some metal polishes will remove inks very easily. So the stuff that I have is extremely mild. Now, I could have polished the chassis to a mere finish, but I really don't want to do that, because it didn't look like that when it came from the factory. And not only that, if I do spend that kind of time polishing, these numbers are definitely going to go missing. So basically just clean the thing up, make it look like it did when it came out of the factory, and that's good enough. Also took the time to clean up the tube shields here as well. Now you'll notice that I've installed the two new potentiometers, one here and one over here. And you'll notice that the wire side is down. Now, on the other ones, the wire side was up. Now, when you're dealing with a non-index shaft, as mentioned earlier, you can mount the potentiometer any old way. Now, the reason that I've done this is because there's an opening in the top of these potentiometers, and you'll find a lot of potentiometers are like that. So if we look right here, you'll see that right here is that opening in the top side. Now, that opening will allow dust inside the potentiometer over time. Dust will settle inside. So by repositioning this and having this on the bottom side really slows that process down. Now, you might be saying to yourself, well, the thing is pretty much a sealed unit. Well, no, there are holes in the thing to breathe. On the bottom side of the cabinet or on the case, there are some large round holes, and that will allow convection cooling to occur within the chassis here. Now, convection cooling is used in a lot of vacuum tube equipment, no need for fans or anything like that, and they really used to oversize the transformers so that they wouldn't get hot. And especially in a device that's going to be used in an industrial application, they don't want the thing to go down. It needs to be very dependable. So what happens is you see that there's holes in the chassis here. Heat from the tube rises and pulls cold air through the bottom portion of the chassis, and it pulls it up through the round holes. There are some, pretty large round holes in the bottom of the case. So by having this convection cooling, it allows the components on the bottom side of the chassis to cool, and it also will draw air up past the tubes and things like that. Well, whenever you have airflow, even from convection cooling, it's going to impose a dust issue, and the dust will circulate in here and then settle on the components. And that's why when I opened this thing up, it was full of dust just from that convection cooling process. So if you ever have the option to put in a potentiometer face down like this, it's always a better idea. There's always dust and it will always try to get inside, but at least, when the dust settles, it won't be settling on the carbon track and you don't end up with a scratchy potentiometer. For the first power up, I have this thing attached to my current limited power supply over here. So there's a Variac isolation transformer and basically dim bulb tester all in one. Those bulbs are acting as current limiting. So I don't know the state of the power transformer in this unit. I imagine it's okay because that 1 amp fuse is fine and looks like there's really no time on this thing. But what I'll do is I'll just turn this on and turn on the bulbs here. They should light up dimly. And they are. So that's how it normally looks. So what I'll do is I'll turn the unit on now. I'll just shut the lamp off here. Here we go. And they're just a little bit brighter, which is normal. Now the thing to watch for is if there is a problem in the high voltage section, when the rectifier tube here warms up, You can tell it's warm by those two little orange glowing strips at the top of the tube right here and here. So if there was a problem in there, and those are glowing orange, these light bulbs would be so incredibly bright right now, it would be washing out the camera. They would be lit up to full brightness, and they're just barely glowing. Now the camera itself makes those bulbs look brighter just the way it is, because the camera is sensitive to that. So everything is fine. So the next stop would be to take this thing out of current limit. So just basically flip this switch over here, and that bypasses the bulbs. And then I'll have a full 120 on this unit here. And I'll do that when I have the oscilloscope hooked up, and we'll see what this thing does on the scope. I figured the proper way to display this older electronic switch would be to have it hooked up to an older oscilloscope. This is a known single trace oscilloscope. In fact, I did a restoration on this oscilloscope not long ago. If you look in my videos list, you'll find the Heathkit O-11 restoration. So I've got this hooked up to the scope through twisted pair only, just like it was intended way back when. What I'll do first is I'll turn on the oscilloscope, and I'll let the oscilloscope warm up. And then after this is all warmed up and set, then we'll go after this thing and turn it on and get everything set up. I've put some wires into the binding post here so I can just clip alligator clips on. I have my signal generator, or my audio generator, hooked up right now, and I have around 100 hertz signal or something like that coming out of the test leads, and that's ready to go as well. And the amplitude's about 50%, so that should be okay. All right, so I'll turn up the intensity here. And there it is. So I can see the scope really hasn't been moved since last time, which is quite a while ago. This is also going to sit on that other bench that I've got going, the restoration bench. All right, so what I'll do now is I'll click on the power supply to the electronic switch. So it's still hooked up to that Variac supply, and it's just through right now. There's no current limit. So here we go. And we'll see what happens. I hooked this up first because I know there's high voltage on that jack and I don't want to touch it. And we have life of some sort happening here. It looks like 2 traces already. Can it get any better? Let's see. Just let it warm for a second. Looks like they're kind of drifting together a bit. All right, so I'll move the balance control. So it is setting at 0. I'll see if I can. Yeah, there it is. They go right together. And that's pointing right at 0. So those tubes have got to be very well matched. You know, again, I say that this thing has probably got almost 0 time on it. So when I move the balance control, it should shift the traces. And as you can see, that's exactly what it's doing. So I can even swap them if I want. Okay, so there we have it. So what I'll do now is I'll grab my cables. I'll just put this down over here. I'll grab my cables and I'll feed an audio signal into this thing. So I'll put the common lead to ground, and I'll just attach this to input A first. We'll start with input A. Gain A, I'll turn gain A up, and look at that. What do I have this? It looks like it's on a square wave. Here, I'll just turn it to a sine. Hey, there we go. So there's a sine, and as you can see, it is not going to lock. So I'm going to need to give this a sync signal. So I'll have to sync the scope to the input A. So I'll just grab an alligator clip over here. Probably should have been a little bit better prepared. I wasn't expecting this thing to come to life like this quick. So here we go. Put this on to sync. Now there's no high voltage on these, so I'm fine at this end here. I'll just clip this, and this should lock the trace, hopefully. And there it is. So, trace A, looking good. So let's see if we can get anything on B, see how B works. So what I'll do is I'll just bridge with another alligator clip, which I've got right here. I'll just clip this to B. So I'm just going to feed the same signal from A to B. So I'll clip this from here to here. Now when I turn up B, I should have the same sine wave on B. And there it is. Look at that. My Heathkit O-11 dual trace oscilloscope. Working very well. It's locked and everything. It's just, wow, that easy. What a nice device. I'm looking forward to putting this thing onto the other restoration bench. And again, that bench is, still being made. And we'll do some tests with this older electronic switch, maybe align some equipment with it. So what I'll do now is I'll put it back to a square wave. Let's see what the square waves look like. So here we go. It's actually surprisingly well. Look at that, looks very well. What you're seeing here is this locking. The oscillator is going to be trying to move here. I can probably demonstrate that, because we're dealing with square waves and another square wave, and then the square wave that's separating the traces here. And you can see this is extending to the top, and that's a dead giveaway that it's the other square wave, because it has to go from bottom to top to make this. So what I'll do is, if I move the frequency control, I might be able to slow this down on one side, and you can actually see the action. There it is. So you can see this, I'll just turn the gain down. That square wave that you see right there is the square wave coming out of that 7N7 tube. And if you want to see the mixing action, all I need to do is turn up gain A, and you'll see a square wave imposed on that particular portion. And this will be the square wave from the signal generator. So I'll turn this up, and there it is. You can see it mixing. Now, if I turn up gain B, the other signal will appear down here. Now, if I just move this a little bit, I can get that to move across the screen a little faster. So you can see how that's happening. So if I speed this up a lot, it will look like two traces. There you go. Now you'll notice that there's a bit of an artifact happening in here, and that's because of the switching. I'm not really too worried about that. I could probably get rid of this little bump on the top, probably with some capacitance adjustment in the circuit. But again, I'm really not worried about it. It's, just kind of a neat old device, kind of a signature of the older device. So what I'll do is I'll just try and slow that particular movement down. And if I get this right in the right spot, I imagine I can probably, there we go. It's basically just one moving across the screen, and I can stop that almost. So not a big deal, having that little thing move across here every now and then. And if I wanted to get used to the artifact, I could just have it really quick moving. And then, of course, we get to that one spot where it stops. So you can really see how this thing works. And it works very well. And surprisingly, look at how square these square waves are for a twisted pair. Amazing. They did a really good job designing this device. So I'll just move this around a little bit. And it'll be like this in the other ranges as well. If I wanted to use a slower signal, I would just change the range switch here. And I would imagine slower signals probably have even a nicer looking square wave. But look at that. It's, a really nice looking wave. So I'll get the sine waves back here again, and I'll just display that again with the sine waves. So put this on here like so, and I'll move this till we can see the square wave doing its thing. So you can see the top portion and the bottom portion. This is our lower trace and our upper trace, and if I shut the bottom one off, you'll see the square, and if I shut the top one off, you'll see the actual oscillator move across the screen. Turning up A will mix the sine wave into that, and as you can see, it's doing that. And if I turn up B, it'll mix the sine wave onto the bottom portion. So you can see how that's creating the two separate signals. And then if I speed it up, then it looks like just a normal dual trace oscilloscope. And with a fine adjustment here, again, you can really slow down that artifact, so it's really not a big deal. Very impressive. Very simple to use as well. And again, of course, if we take the sync control off, there'd be just no locking this at all. So Very important to have an external sync input in order to use something like this. So all in all, big thumbs up for that device. That's working really well. I'm looking forward to doing some future experiments with this thing and aligning some gear with you guys. Thanks for stopping by the lab today. Hope you enjoyed this episode involving this Sylvania electronic switch. If you did, you can let me know by giving me a big thumbs up and hang around. There'll be many more episodes coming like this in the future. We'll be taking a look at solid state and vacuum tube electronics alike. And of course, as usual, we'll dive right into it and I'll do the explanation and lots of restorations. If you haven't subscribed yet, you may want to do that as well. If you're interested in taking your electronics knowledge to the next level, I have an ongoing electronics course on Patreon right now. So I'll have that link just below this video right about here in the description. If you do go there, check out the community section. So click on the little community tab and there's many people there that have uploaded their projects. And we have a build along going along right now. So we're building a bunch of projects together. So it's a really interesting little area to check out. I'd also like to say thank you to all my patrons at this point. It's only been a half a year and I'm already just about halfway to my goal. The closer I get to my goal, the more I can be here on YouTube making videos. So really what this is doing is just helping me afford the time to be here so I can make videos for you guys. So again, thanks a lot. Big thumbs up to all you guys as well. So I'll see you next time. Take care. Bye for now.